Tonight, we're going to explore one of the most humbling truths in all of modern science. Humanity, despite every dream of starships and distant colonies, will almost certainly never leave the solar system. Voyager 1, launched in 1977, is the fastest object we have ever sent into the dark, traveling at 17 kilometers every second. At that speed, reaching the nearest star, Proxima Centauri, just 4.24 light-years away, would take roughly 70,000 years. 70,000 years to reach the closest neighbor in a galaxy of 100 billion stars. And yet distance may not be the real reason we are trapped here. Hidden beneath the vastness of space is a deeper problem, one that turns every proposed path to the stars into a dead end, no matter how advanced the technology becomes. The distance is not the only wall. The speed of light is a wall. Energy is a wall. Biology is a wall. Economics is a wall. And the silence of the cosmos may be the final wall, the one that tells us every civilization meets the same edges we do. By the end of tonight, you're going to understand why those 4.24 light years are far more than a number, why the layered barriers of distance, energy, and fragility compound into a confinement no realistic technology can break, and why Earth may not be a prison at all, but the only home the universe was ever going to allow us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. 70,000 years. Let that number sit for a moment. Not 70,000 miles. Not 70,000 days. 70,000 years of continuous travel just to drift past the nearest star, which would not stop, would not greet us, would not even notice us passing. And the spacecraft making that journey is already out there. It has been flying for nearly half a century. It is moving faster than any object humanity has ever launched, and it has barely left the neighborhood. That is the wall we are up against. To understand how strange that is, it helps to remember how far we have already come. The story of humanity reaching into space is genuinely one of the most remarkable things our species has ever done. In 1957, a small metal sphere called Sputnik beeped its way through low Earth orbit, and the space age began. Just 4 years later, in 1961, Yuri Gagarin became the first human being to leave the planet, circling the Earth once and returning alive. And then, in 1969, Apollo 11 carried 2 people to the surface of the moon. Neil Armstrong stepped out onto the lunar dust, and for a moment the entire planet watched together. That was real. That mattered. The engineering was genuine, the courage was genuine, the achievement was permanent, but the moon is 384,000 kilometers away. Light crosses that distance in just over a second. On the scale of even our own solar system, the moon is the end of the driveway. We walked to the end of the driveway and called it a giant leap for mankind, and in every meaningful human sense, it was. But the cosmos does not measure things in human senses. After Apollo, the focus shifted. Crewed missions to the moon ended, and the age of the probe began. Uncrewed spacecraft carried instruments to Mars, to Jupiter, to Saturn. They mapped atmospheres, measured magnetic fields, photographed moons no one had ever seen clearly. The data they sent back changed planetary science permanently, and one of those spacecraft kept going. It did not stop at Saturn. It did not stop at the edge of the solar system. It is still going today. Voyager 1 launched in 1977. It has been in continuous flight for nearly 50 years. It is moving at 17 kilometers per second. That is roughly 61,000 kilometers per hour, faster than any bullet, faster than any aircraft, faster than anything humans had built before it. At that speed, you could circle the entire Earth in less than 12 minutes. And after nearly half a century of flying at that speed, Voyager 1 is now somewhere between 20 and 24 billion kilometers from Earth. That number is genuinely difficult to hold in the mind. 20 billion kilometers. Think of it this way. Light, the fastest thing in the universe, traveling at 300,000 kilometers per second, takes over 20 hours to reach Voyager. A radio signal sent from Earth right now will arrive at the spacecraft sometime tomorrow. That feels enormous. It is enormous. It is the farthest any human-made object has ever traveled. And here is where it gets strange. In the context of the galaxy, Voyager 1 has gone almost nowhere. The nearest star to our sun is Proxima Centauri, 4.24 light-years away. A light-year is the distance light travels in a single year, roughly 9.46 trillion kilometers. Proxima Centauri is 40 trillion kilometers from us. Voyager, after 50 years, has covered about 22 billion kilometers. To reach Proxima Centauri at its current speed, Voyager would need roughly 70,000 more years of travel. 70,000 years. Modern human civilization, with cities and agriculture and writing and mathematics, is only about 10,000 years old. We would need 7 civilizations laid end-to-end in time just to complete the journey. And Voyager is not even aimed at Proxima Centauri. It is heading in a different direction entirely. If it were on course, if every calculation were perfect, it would eventually drift into the outer edges of that system, not with a landing, not with a greeting, but with a silent passage through the dark. No deceleration, no arrival, just a dead spacecraft crossing through a foreign solar system and continuing onward into the void. Not a visit. A flyby. A flyby of a star we cannot reach. That is the actual state of human interstellar capability today. The furthest object we have ever launched, traveling faster than any human engineering has ever managed, will drift within range of another star system in approximately 40,000 years, and even then, it will not stop. It will pass through and keep going. We sent something to the stars. In a sense, and even that achievement, the truest form of leaving the solar system humanity has ever managed, takes geological timescales to amount to a flyby. After 50 years, Voyager has taught us something more than science. It has given us a precise, unflinching measurement of our own situation. We are fast by human standards. We are slow by cosmic ones. We are far from home by human standards. We are still at home by cosmic ones. The distances between stars are not just large. They are not large the way the Pacific Ocean is large, or the way the Sahara Desert is large, where large means a great deal of effort and a great deal of time. They are large in a way that defeats those categories entirely. They make the words effort and time feel irrelevant. And Proxima Centauri is the closest star. There are 100 billion more. This is where the problem stops being about engineering and starts being about something deeper. It is not just that we lack a fast enough spacecraft. It is that the gap between what we have and what interstellar travel would require is not a gap that closes gradually. It is not a problem of needing a better engine or more fuel or a few more decades of research. But the question of what it would actually take to cross that gap, and why every proposed answer runs into walls that go far beyond rocket science, that is still ahead. Lift your gaze from that drifting probe for a moment. Lift it past the outer planets, past the edge of the solar system, up to the night sky itself. On a clear night, far from city lights, you can see thousands of stars. They look close. They look like they belong to the same room as you, scattered and glittering just overhead. Your eye reads them as near, as reachable in principle. That reading is wrong. It is the greatest optical illusion in existence. The stars are not close. They are not in the same room. They are not even in the same neighborhood by any measure the human brain was built to manage. And the gap between how they look and how far they actually are is so vast that closing it in your mind requires a kind of deliberate, systematic work. So let us do that work together. The nearest star to our sun is Proxima Centauri. You already know its name and its distance from what came before, but knowing the number is not the same as understanding it. 4.24 light-years, roughly 40 trillion kilometers. The unit alone should stop you. 40 trillion. Your brain processes that number the same way it processes any number too large to hold. It registers something enormous and then quietly lets it go. We need a different approach. We need to shrink it. Imagine the entire solar system compressed down to the size of a coin. Not the orbits of the outer planets. The whole system. Sun to Neptune, everything. Compressed to something you could hold between your fingers. At that scale, Proxima Centauri would be a second coin sitting about 200 meters away. 2 football fields. You could see the first coin from where you stood. You could not reach the second one in a sprint. And this is the closest star. At that same scale, the center of our galaxy, which the European Space Agency's Gaia mission has helped map in extraordinary detail with over 1 billion individual stars charted in 3 dimensions, that center would be halfway around the actual Earth. Not 2 football fields, halfway around the planet. Let that geography settle. The nearest star is 2 football fields away at the coin scale. The rest of the galaxy is the rest of the world. Now come back to real distances. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. That is the baseline unit astronomers use for measuring distances inside a solar system. Voyager traveled for over 4 decades to reach the outer boundary of our solar system, a journey measured in tens of astronomical units. And still, our solar system on the coin scale is smaller than your fingernail. The space between that fingernail and the second coin is not measured in astronomical units. It is measured in light years. In the distance light travels across an entire year of constant motion. Here is where the numbers become cognitive events rather than statistics. 1 light year is roughly 9.46 trillion kilometers. Proxima Centauri is 4.24 light years away. So the distance to the nearest star is not 1 light year, not 2. It is 4 years of light's travel, where light moves at 186,000 miles per second and never stops and never slows down. The star you see on a clear night as a point of light is, at minimum, that far from you. Most are much farther. And here is what it costs at the speeds we can actually achieve. Voyager is moving at roughly 17 kilometers per second. That is genuinely fast. By any human standard, it is extraordinary. But at Voyager's speed, the trip to Proxima Centauri would take approximately 70,000 years. Not decades, not centuries. 70,000 years. And Voyager is not even aimed there. The coin 2 football fields away might as well be on the other side of the universe. But here is where it gets strange. Even if we imagine something far beyond Voyager, something traveling at speeds we have never achieved and cannot yet build, the problem does not disappear. It shrinks, but it does not vanish. If you could somehow accelerate a spacecraft to 1% of the speed of light, a speed roughly 600 times faster than Voyager, the trip to Proxima Centauri would still take more than 4 centuries, 400 years of travel. For the nearest star, if you push to 10% of the speed of light, something that would require energy expenditures we have no current means to produce, the journey drops to about 40 years. Still longer than a human working career. Still longer than most human lives. And that is Proxima. That is the easy case. Not a nearby destination, not a manageable journey. The closest star in the sky. The brain keeps trying to reframe this as an engineering problem. A problem of speed, of fuel, of technology, of time. But the numbers resist that reframing. The void between stars is not something you close by going faster. You reduce the crossing time. You do not eliminate the crossing. And the crossing, even reduced, consumes human lifetimes at the speeds physics allows with anything close to plausible technology. This is what the night sky hides. It offers you thousands of points of light arranged like they are waiting to be visited. It gives the impression of a reachable field. What it does not show you is the 40 trillion kilometers of nothing between you and the nearest one of them. The darkness between the stars is not a backdrop. It is the substance. It is almost everything there is. Distance is the first wall, and it is not a wall you scale with a longer ladder. But distance, vast as it is, turns out to be only the beginning of the problem. The deeper barriers are not written in kilometers. They are written in physics itself. The laws of physics are not suggestions. They are the architecture of reality itself. And they begin with one absolute rule. Nothing with mass moves at the speed of light. This is not a current technological limitation. It is a structural feature of the universe, established by Einstein's theory of special relativity and confirmed by more than a century of precise experimental measurement. The speed of light is roughly 300,000 kilometers per second. That number sounds like freedom. It is not. Even if you could somehow reach that speed, Even if every constraint of engineering and energy dissolved overnight, Proxima Centauri would still take 4.24 years to reach. One way. That is the ceiling. And nothing we build can touch it. Here's what scientists believed for a while. If the speed limit was set by physics, perhaps exotic physics could find a way around it. Warp drives, wormholes, quantum entanglement propulsion. These were not science fiction proposals dismissed out of hand. From 1996 to 2002, NASA ran a formal research effort called the Breakthrough Propulsion Physics Program, specifically tasked with investigating whether any theoretical mechanism could circumvent conventional rocket physics. The program was serious. The scientists were serious. Mark Millis, who directed the effort, spent years evaluating the most optimistic theoretical proposals that could be constructed under known or speculated physics. The conclusion was not encouraging. Even the most favorable theoretical scenarios, the ones that stretch speculation to its limit while still remaining connected to physics at all, would require energy equivalent to the entire mass energy of Jupiter. Not Jupiter's output. Not the energy Jupiter radiates. The mass energy contained in Jupiter itself, converted completely to propulsion, to send a small probe to the nearest star. Jupiter has a mass of roughly 1.9 times 10 to the power of 27 kilograms. Converting that mass entirely to energy via Einstein's equation yields a number that dwarfs everything humanity has ever produced, by a factor of billions, multiplied again by billions. The Breakthrough Propulsion Physics program ended in 2002. Not because the idea was abandoned, but because the physics would not cooperate. But forget exotic physics for a moment. What can we actually do right now? We have a benchmark. In 2018, NASA launched the Parker Solar Probe, and it became the fastest human-made object ever built. At its closest approach to the Sun, using the Sun's own gravity to accelerate, it reached 195 kilometers per second. That is extraordinary by every human standard. It would cross the continental United States in roughly 16 seconds, and it is still only 0.065% of the speed of light. At that speed, the journey to Proxima Centauri would take approximately 6,500 years, and that number uses a gravitational assist from the Sun that we cannot replicate for interstellar travel. Once you leave the solar system, there is no second star close enough to borrow gravity from on the way out. But here is where it gets strange. Even if we could go much faster, even if we could reach speeds far beyond anything we have built, a different law would step in to destroy the plan. Konstantin Tsiolkovsky wrote it down in 1903, the rocket equation. It is simple enough to fit on a single line and devastating enough to have closed the door on interstellar travel for every generation since. The principle it encodes is this: the fuel required to accelerate a rocket grows exponentially with the desired final velocity. Not proportionally, not steeply, exponentially. Think about what that means at interstellar scales. To reach just 10% of the speed of light and then decelerate enough to actually stop at the destination rather than fly through it at full speed, the mass ratio required is roughly 10 to the 9th power. 1 billion kilograms of fuel for every single kilogram of payload. Not 1 billion kilograms total. 1 billion per kilogram of what you are actually trying to deliver. A 1-ton scientific instrument would require 1 billion tons of fuel. That is not a matter of building bigger rockets. That is the arithmetic of the universe working against you. For comparison, the Saturn V, the most powerful rocket ever successfully launched, the vehicle that carried human beings to the moon and back, achieved a final velocity of roughly 0.004% of the speed of light, barely enough to escape Earth's gravity. That was our greatest engineering achievement in propulsion, and it moved us to a fraction of a fraction of a fraction of the speed we would need. Not a step toward interstellar travel, a step toward the end of the driveway. Dr. Jeffrey Landis at NASA's Glenn Research Center has done the calculation for what the best current technology can actually achieve. Ion drives powered by nuclear reactors represent the upper edge of what is plausible in the foreseeable future. No engineering breakthroughs assumed, no speculative physics invoked. Just the best of what we have and can reasonably project. At that performance level, A journey to Proxima Centauri would take 40,000 years, and it would require more plutonium than currently exists on Earth. Not more than we have stockpiled. More than exists on the planet. What about fusion rockets? They do not exist yet. But suppose they did. Suppose we mastered the same nuclear process that powers the sun. Deuterium and tritium fuse together to release enormous energy. Even a perfect fusion drive, extracting the maximum energy from fuel that physics allows for this reaction, would require tens of thousands of tons of propellant for a centuries-long journey. Centuries. And that assumes a drive we have not built, using fuel we would need to produce in quantities we have never attempted. For a mission duration no human institution has ever sustained. The exponential nature of the fuel curve is the real wall. Each small step closer to light speed does not cost a proportionally larger amount of fuel. It costs catastrophically more. Doubling your speed does not double your fuel requirement. It can square it, cube it, compound it in ways that quickly outrun any conceivable fuel source. The rocket equation does not care about ambition. It does not care about need. It applies with perfect indifference to every proposal anyone has ever written down, and it has never once been wrong. The speed barrier is not a problem waiting for a clever engineer. It is not a gap that better materials or more efficient engines will eventually close. The physics that governs propulsion, the physics that sets the speed of light as a ceiling, the arithmetic that compounds fuel costs into absurdities, these are not temporary obstacles. They are the structure of the problem itself. We are not behind the curve on interstellar travel. We are working inside a universe that was built with these rules already in place. And yet the deepest complications have not arrived yet. Speed and fuel are the walls that physics builds in the abstract. The walls built by the actual conditions of interstellar space are still ahead. Smart people have tried specific solutions. That is worth acknowledging. The history of proposed interstellar propulsion is not a history of casual daydreaming. It is a history of serious engineers, serious institutions, and serious money applying genuine rigor to the problem. And one by one, each proposal has arrived at its own private wall. The first serious attempt came from the British Interplanetary Society. Between 1973 and 1978, a team of engineers worked on a project called Daedalus. The goal was concrete and specific. Design an unmanned fusion-powered probe capable of reaching Barnard's star, one of the closest stars to our solar system, in 50 years. Not in principle, on paper with real numbers, real engineering constraints, real material specifications. They worked it out. The design required a two-stage fusion rocket. The total mass of the craft, 54,000 tons. That is roughly the mass of a naval aircraft carrier. Not the payload, not the fuel, the craft. And the fuel it required was 30,000 tons of deuterium, a heavy form of hydrogen, plus 20,000 tons of helium-3, a rare isotope that barely exists on Earth in usable quantities. To obtain enough helium-3, the Daedalus team concluded you would need to mine it from the atmosphere of Jupiter, which would require a space-based industrial infrastructure, which would itself take centuries to build. The design was not wrong, the physics was sound, the engineering was coherent, and it was completely unrealizable. In 2009, a new team revisited Daedalus under the name Project Icarus. The intent was to update the concept with modern knowledge, modern materials, modern computational models. Dr. Richard Obusi, one of the project leads, stated the conclusion plainly. The energy requirements remain prohibitive even under the most optimistic assumptions. Not optimistic in a loose sense, optimistic in the technical sense, meaning assumptions that favor the concept at every turn, that grant every reasonable benefit of the Tao. Even then, the project requires breakthroughs in exotic physics that may not be possible at all, and beneath both projects sits a harder problem. Fusion, the process Daedalus and Icarus propose to harness, does not yet work on Earth. Not reliably, not practically. Humanity has been attempting controlled fusion for more than 70 years. The ITER fusion reactor, currently under construction in France, has been in development since 2007. Its budget has exceeded 20 billion euros. Its first plasma is projected for 2025 at the earliest. When it runs, it will run for minutes at a time. It will consume more energy than it produces. In December 2022, the National Ignition Facility at Lawrence Livermore achieved something that made international headlines: fusion ignition. A genuine milestone. But the total energy fed into the system, accounting for the lasers, the infrastructure, the full chain of energy input, exceeded the energy released by a factor of 100. Fusion ignition, yes. Net energy gain, nowhere close. The dream of compact fusion powerful enough to drive a starship is a dream resting on a foundation that does not yet exist. But here is where it gets strange. There was a concept that seemed to solve the fuel problem entirely. In the 1960s, physicist Robert Bussard proposed what he called an interstellar ramjet. The idea was elegant. Instead of carrying fuel, the spacecraft would scoop hydrogen from the interstellar medium as it traveled, fusing it continuously to generate thrust. No fuel tanks, no mining Jupiter. The universe itself would be the fuel supply. Dr. Daniel Whitmire analyzed the physics carefully. The interstellar medium, the thin gas that fills the space between stars, contains roughly 1 atom per cubic centimeter, not 1 atom per teaspoon. 1 atom per cubic centimeter, which is a space roughly the size of a sugar cube. At that density, to collect enough hydrogen to generate meaningful thrust, the scoop would need to be thousands of kilometers wide. And then Whitmire found the deeper problem. The drag created by pushing through the interstellar medium to scoop the hydrogen would exceed the thrust generated by burning it. The engine would slow the ship down faster than it could accelerate it. The ramjet does not fail because we cannot build it. It fails because the physics works against it. Whitmire's conclusion: engineering pure fantasy. Antimatter propulsion carries a different kind of appeal. It represents the theoretical peak. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into energy. No chemical reaction comes close. No fusion reaction comes close. If you could store antimatter and release it in a controlled way, you would have the most efficient fuel physically possible. Wait, consider what actually producing antimatter requires. The Large Hadron Collider, the largest and most powerful particle accelerator ever built, produces approximately 10 nanograms of antimatter per year. A nanogram is 1/1000th of a gram. All the antimatter ever produced by humanity combined would not power a household light bulb for a single second. And each nanogram costs millions of dollars to produce. Fueling an interstellar mission would require kilograms of antimatter. At current production rates, that quantity would take more than 1 billion years to accumulate. Not $1 billion, 1 billion years. And even if the production problem was somehow solved, the storage problem remains. Antimatter annihilates on contact with ordinary matter, which means every atom of the container. To store it, scientists use devices called penning traps, which suspend antiparticles using powerful magnetic fields, isolated from all physical contact. Penning traps currently hold antiparticles for minutes to hours before the particles are lost. Dr. Gerald Smith of Pennsylvania State University calculated that the magnetic fields required to store antimatter for an interstellar journey would consume more energy than the antimatter itself could provide. The storage mechanism defeats the fuel before the ship leaves the solar system. The most recent major proposal takes a different approach entirely. Breakthrough Starshot, announced in 2016 with backing from investor Yuri Milner and the endorsement of Stephen Hawking, attracted $100 million in initial funding. The concept was to skip large spacecraft entirely. Instead, send gram-scale probes, each roughly the mass of a paperclip, equipped with a light sail, and accelerate them with a ground-based laser array to 20% of the speed of light. At that speed, they would reach Proxima Centauri in about 20 years. The signal reporting back would take another 4.24 years to arrive, a quarter century total for a flyby of the nearest star. The laser array required to achieve that acceleration would need to deliver 100 gigawatts of power, France's entire national electrical output, focused, continuously, over the acceleration phase. Dr. Philip Lubin of UC Santa Barbara, one of the concept's serious proponents, acknowledged that even a perfectly engineered beam would spread to thousands of kilometers wide by the time it reached the probe at any significant distance. Keeping enough energy on target is a problem that scales against you. And then, the acceleration itself. To push a gram-scale probe to 20% of light speed in a reasonable time, the probe would experience approximately 60,000 times the gravitational force of Earth. 60,000 G. No electronics conceived of today could survive that. The probes the system is designed to launch would be destroyed in the act of launching them. The probes also cannot slow down. There is no mechanism to decelerate at the destination. They would pass through the Proxima Centauri system in a matter of hours, gathering whatever fragmentary data their surviving instruments could capture before the system receded behind them forever. A flyby of the nearest star at enormous cost, delivering hours of data with no ability to stop, orbit, or return. Ion drives, the most efficient propulsion technology humanity has actually used in space, round out the picture. NASA's Dawn mission used ion propulsion to explore the asteroid belt. Ion drives are genuinely efficient. They extract more thrust from each kilogram of fuel than any conventional rocket. They are also extremely slow to accelerate, generating thrust measured in millinewtons, roughly the force of a feather resting on your palm. Dawn spent years patiently crossing the inner solar system. Applied to interstellar distance, the numbers do not change. Ion propulsion is a tool for the solar system. It has nothing to say to the gap between stars. Each of these concepts was developed by real scientists doing real work. Each was taken seriously by serious people. Each is independently impossible, not because the engineers made errors, but because each proposal reached, from a different direction, the same underlying terrain. The fuel problem, the energy problem, the physics that was already in place before anyone started writing the proposal, and the actual conditions of the space between stars, the collisions, the radiation, the void itself, have not yet been counted. Those walls are still ahead. Those walls were not just theoretical. Physics keeps building them in every direction you look. The science fiction arguments come next. They always do. Someone mentions warp drives, someone mentions wormholes. These are not idle fantasies. They are grounded in real mathematics, real physics, real publications, and they deserve a serious answer. Miguel Alcubierre, a physicist working from Einstein's field equations, showed in 1994 that general relativity does not actually forbid faster than light travel. Not the object itself moving faster than light. The space-time around the object contracting in front and expanding behind. So the craft rides a wave without technically accelerating past the universal speed limit. The mathematics worked. The equations permitted it. Here is where it gets strange. Making it real requires exotic matter. Not a substance we have not yet synthesized in a laboratory. A substance with negative energy density. Something that pushes outward where normal matter pulls inward. We have never observed it. We have no confirmed evidence it exists. Dr. Michael Fanning and Dr. Larry Ford analyzed the requirement carefully and showed the exotic matter demand was not a minor technical detail to be engineered around. It was the foundation the entire concept rested on. Dr. Sergei Krasnikov went further. He calculated the amount of negative energy required to generate a functional warp bubble. The number he arrived at exceeded the total positive energy in the entire observable universe. Not a large country's energy output. The entire observable universe. That is not an engineering problem. That is the physics telling you no. Recent work by Dr. Alexei Bobrik and Dr. Gianni Martire claimed to reduce the energy requirements significantly. Their proposals attracted genuine scientific attention. But the reduced energy solutions still require energy equivalent to the mass of Jupiter converted entirely to fuel, and they only function at sublight speeds. A warp drive that cannot exceed light speed does not solve the problem it was invented to solve. Wormholes follow the same pattern. Dr. Kip Thorne, one of the physicists who worked out their properties most carefully, showed that traversable wormholes would also require exotic matter to remain stable. Without it, any wormhole collapses faster than light can cross it. You would not pass through. you would be caught in the collapse. And quantum effects near the throat of any wormhole generate a firewall of radiation intense enough to destroy anything attempting passage. Not a hazard that better shielding addresses. A physical consequence written into the geometry of the space itself. Every exotic shortcut closes the same way. The mathematics permits something. The matter required to build it does not exist. And the quantities demanded, even theoretically, exceed what the universe appears to contain. The M drive tried a different path entirely. No exotic matter, no faster-than-light ambition, just thrust without propellant, generated by bouncing microwaves inside a closed metal cavity. Initial tests at NASA's EagleWorks laboratory seemed to show something. A small but detectable thrust. The results were published. The attention was immediate. Wait. The Technical University of Dresden ran careful follow-up experiments. What they found was not thrust. It was thermal expansion of the cavity walls and magnetic interactions between the testing equipment and the surrounding environment. When these artifacts were controlled for, the thrust disappeared. The M drive would require violating the conservation of momentum, one of the most thoroughly tested principles in all of physics. It does not work. Every exotic escape hatch, when examined honestly, leads to the same destination. Impossible resources, unobserved matter, violated conservation laws, or failed experiments. So the question becomes civilizational. Not whether any particular concept fails, but whether the problem is simply one of scale. Build bigger, use more energy, develop longer. Perhaps what is required is not a clever trick, but an enormous sustained commitment. The numbers here are equally stark. Human civilization currently uses approximately 20 terawatts of energy in total. Every power plant, every vehicle, every factory, every heated building on Earth, added together. That is our full output. Accelerating a spacecraft of 1,000 tons to 10% of the speed of light, and then decelerating it at the other end, requires roughly 10 to the 21st power joules of energy, a number that does not land easily on its own. Translated, it equals approximately 15 years of total human energy production. Not from one country, not from one continent, from every human energy source on the planet, running continuously for 15 years, directed entirely at one mission. And that energy has to be delivered in space. Fuel must be lifted out of Earth's gravity well, or orbital infrastructure vast enough to store and deploy it must be constructed first. The mass problem from earlier sections does not disappear. It compounds. The communication problem compounds separately. As a spacecraft travels farther from Earth, the energy required to transmit data home grows with the square of the distance. Voyager 1, currently more than 20 billion kilometers away, requires a 70-meter deep space network antenna and 20 kilowatts of transmission power just to receive its faint signal. That is already an enormous infrastructure dedicated to one old probe, traveling at a small fraction of the required speed. A spacecraft at Proxima Centauri would be 17 times farther than Voyager is now. The energy required for the same data rate would be nearly 3 million times greater. The New Horizons mission, launched in 2006, reached Pluto after 9.5 years of flight. From Pluto, it transmitted data at roughly 1 kilobit per second. That sounds modest. From Proxima Centauri, that same transmission rate would drop to less than 1 bit per day. 1 bit per day. Without fundamental breakthroughs in antenna technology, communication alone would render any returned data scientifically meaningless. The radiation problem sits beyond the communication problem. The heliosphere, the vast bubble of solar wind that surrounds our solar system, extends to about 120 astronomical units from the Sun. Beyond that boundary, cosmic radiation, high-energy particles accelerating from distant supernovae, and other violent events intensifies dramatically. Inside the heliosphere, the Sun's own outflow deflects much of it. Outside, the ship is exposed. Dr. Eugene Parker, the physicist whose name now graces the Parker Solar Probe, calculated what shielding against that radiation would require for a crewed mission to Proxima Centauri. Generating a magnetic field strong enough to deflect the relevant cosmic rays throughout the journey would demand more power than a nuclear power plant produces, running continuously for centuries. That reactor has mass. Mass requires more fuel. More fuel adds more mass. The vicious cycle compounds. More shielding mass means more fuel needed, which means more mass to shield, which means more fuel again. Here is where the civilizational frame becomes unavoidable. Physicist Nikolai Kardashev proposed a classification for civilizations based on their total energy use. A Type 1 civilization harnesses all the energy reaching its planet from its star. A Type 2 civilization harnesses the total output of the star itself. Humanity currently sits at approximately 0.73 on this scale. We are not yet a Type 1 civilization. We use a fraction of the solar energy reaching Earth. Credible interstellar travel, by most analyses of the energy requirements, demands Type 2 capability, access to the full output of an entire star. The Kepler Space Telescope surveyed more than 150,000 stars looking for signs of Dyson sphere construction. The megastructure a Type 2 civilization would need to capture its star's total output. It found no convincing signatures. Not one candidate that held up to scrutiny. Either no civilization in that survey region has reached Type 2, or no one reaches Type 2 at all. The pattern is consistent across every frame. Individual propulsion concepts fail on physics. Civilizational energy budgets fail on scale. The energy floor for interstellar travel appears to sit above the energy ceiling of any single star civilization. And that is before the journey itself begins. All of that sits above the journey. The energy ceilings, the propulsion walls, the civilizational scale of the problem. But underneath all of it, before the spacecraft is built, before the fuel is calculated, before any of those questions are answered, there is a simpler and more unsettling one. Can the human body survive the trip at all? We did not evolve to live in space, we evolved on Earth, tuned to its gravity, its atmosphere, its radiation levels, its rhythms of light and dark. Every system in the human body was shaped by 4 billion years of life on this particular planet. Not a planet like Earth, this planet. And the moment we leave it, the body notices. NASA gave us the clearest evidence of that in a study that was genuinely unprecedented. Astronaut Scott Kelly spent 1 year aboard the International Space Station. His identical twin brother, Mark Kelly, stayed on Earth. Same genetics, same baseline biology, 1 year apart. When Scott returned in 2016, researchers compared the brothers in extraordinary detail. The results were not what anyone expected. 7% of Scott's DNA changed the way it expressed itself while he was in orbit. Not damage in the conventional sense, not a mutation, something subtler and in some ways more troubling. The machinery that reads the genetic code and decides which proteins to produce, which systems to activate, which cells to build, had shifted. And when Scott came home, most of those changes faded, but not all of them. Some of the alterations to his gene expression never returned to baseline. 1 year. Partially irreversible. But the gene expression finding was only the beginning. Scott's telomeres changed in orbit. Telomeres are the protective caps on the ends of chromosomes, the structures that keep genetic information intact as cells divide. They shorten as we age. In space, Scott's lengthened, which initially seemed positive. Then he came home. They did not simply return to their prior length. They shortened dramatically, and they shortened fast, beyond what his Earthbound twin experienced over the same period. The cellular aging process had been disrupted in both directions, stretched, then snapped back harder than before. His cognitive performance declined measurably. His cardiovascular system deteriorated. His immune system, rather than functioning as a defense, became hyperactive, turning inward and beginning to attack his own body. His gut microbiome, the ecosystem of microorganisms that supports digestion, immunity, and a range of neurological functions, was devastated. 1 year, in low Earth orbit, still partially sheltered by Earth's magnetic field. That detail matters enormously. The International Space Station sits inside the outer edge of the Van Allen belts, the magnetic cocoon Earth generates around itself. It is not full protection, but it is protection. Scott Kelly was never truly exposed to what a traveller beyond Earth's magnetic influence would face. Dr. Dorit Donoviel, a researcher at the Translational Research Institute for Space Health, has studied what happens to that exposure as you move outward. Her analysis is stark. Radiation during a Mars mission, a mission measured in months, would raise a traveller's cancer risk by up to 20%. For an interstellar journey lasting decades or centuries, the accumulated dose would not be a medical complication to monitor and manage. It would be uniformly fatal. Outside the protective reach of Earth's magnetic field, two categories of radiation compound their damage continuously. Cosmic rays arrive from all directions, high-energy particles streaming in from supernovae and other violent processes across the galaxy. Solar energetic particles burst outward from the sun in unpredictable eruptions. Together, they penetrate the body, damaging DNA, degrading the nervous system, accumulating in the heart muscle and the brain. We covered in an earlier section what the shielding requirements for a crewed interstellar mission would demand from an energy standpoint. But the biological reality is the other side of that same equation. The radiation does not wait for the engineering to catch up. And radiation is only one of the forces rewriting the body in space. Bone does not care about ambition. It responds to the forces placed on it. On Earth, gravity pulls the skeleton down constantly, and the body continuously rebuilds bone tissue in response to that load. Remove the load, and the body stops rebuilding. JAXA, the Japan Aerospace Exploration Agency, has documented the rate carefully. Astronauts lose 1 to 2% of their bone mass every month in microgravity. After a year, the cumulative loss exceeds what a typical elderly person experiences across an entire decade. Think about what that means over centuries. Bones would not merely weaken, they would dissolve. The calcium leached from them would have to go somewhere. It accumulates in the bloodstream. It precipitates in the kidneys, forming stones. The skeletal system that holds the human body upright, that protects the organs, that anchors the muscles, would gradually consume itself from within. Daily exercise routines, the standard countermeasure on the ISS, slow the process. They do not stop it. Muscles atrophy despite those routines. The cardiovascular system restructures itself around a weightless load, which means it deteriorates in the presence of gravity if it ever encounters gravity again. These are the known walls, the ones we have measured and documented in the controlled context of the space station. But here is where it gets strange. All of the countermeasures, the exercise, the shielding, the monitoring, the pharmaceutical interventions rest on one foundational assumption, that there are humans aboard the ship capable of applying them. And for a multi-generation mission, that assumption leads somewhere that science fiction has largely avoided looking directly at. Reproduction in space does not work the way it does on Earth. Experiments conducted on the International Space Station have examined what microgravity does to mammalian reproductive biology. The results are not ambiguous. Sperm count in microgravity drops to near zero. The mechanisms by which sperm develop and function are gravity-dependent in ways that were not fully understood until the absence of gravity revealed them. Embryonic development is severely impaired. Mice subjected to space simulation conditions have shown devastating birth defects at rates that preclude any reasonable expectation of viable offspring. Dr. Joseph Tash, a researcher at the University of Kansas Medical Center who has studied reproductive biology in spaceflight conditions, reached a conclusion that is difficult to soften. Normal human reproduction may be impossible in zero gravity. That sentence quietly ends the generation ship. The generation ship is the science fiction solution to the time problem. If you cannot reach another star in one human lifetime, send enough people that they can have children, and those children can have children, and eventually, across many generations, someone lands. It is a compelling idea. It assumes that the ship is a viable habitat for the full human life cycle. Birth, growth, development, reproduction. What the biology suggests is that the foundational step, reproduction itself, may not function in the environment a generation ship would provide. Not for lack of will, not for lack of resources. because zero gravity disrupts the cellular and physiological processes that human reproduction requires. Whether artificial gravity, generated by rotating the ship, could rescue, this is a question the research has not fully answered. It is an open possibility, but it is not a solved one. And the other walls, the radiation, the bone loss, the immune dysfunction, the cellular changes that do not fully reverse, remain regardless of what rotation does for reproduction. Scott Kelly spent 1 year in low Earth orbit, closer to home than any interstellar mission could dream of being, inside a magnetic shield that would not exist beyond the heliosphere. And the body he came home with was measurably different from the one that left. Some of those differences never went away. The biology had not even begun to face what the deeper journey would require. That body, the one Scott Kelly brought home after a single year, had barely encountered the full weight of what an interstellar crossing would demand of a person. It had not traveled with hundreds or thousands of others through a sealed world. It had not tried to sustain an entire civilization in a metal shell. It had not endured the slow collapse of the invisible biology that makes human survival possible in the first place. Because here is what the generation ship concept assumes, quietly, without stating it directly. It assumes that the humans inside the ship remain human, not just anatomically, microbiologically, psychologically, ecologically. It assumes that the systems layered beneath and around individual bodies, the trillions of microorganisms that colonize every surface of every person, the social structures that keep minds intact, the closed web of air and water and food that a sealed vessel must sustain, it assumes all of those systems hold together, for decades, for centuries, for whatever the crossing requires. They would not hold. The human body is not a single organism. It is an ecosystem. Trillions of bacteria, viruses, and other microorganisms live in and on every person, most of them essential to digestion, immune function, and basic cellular maintenance. These microbial communities are not static. They are constantly refreshed and rebalanced by contact with the outside world, with soil, with other people, with the endless biological variety of a living planet. Cut that contact off, and the microbiome begins to degrade. Dr. Hernan Lorenz at the J. Craig Venter Institute has tracked what happens to astronaut microbiomes even on short missions. The changes are dramatic. Bacterial populations shift. Potentially dangerous strains become dominant. The microbial balance that a healthy immune system depends on begins to tip. On a sealed interstellar ship, that tipping would not stop. It would compound. Mutations would accumulate. Strains would evolve in directions no medicine could anticipate. A closed spacecraft would become a petri dish, and the experiment running inside it would not be the one anyone designed. Consider what this means at the scale of a pandemic. In 1918, the Spanish flu killed somewhere around 50 million people across the entire surface of the Earth. A planet with sunlight and open air, and the ability to isolate the sick and resupply the healthy. On an interstellar ship, there is no isolation. There is no outside. A single outbreak, with no possibility of intervention, could kill everyone aboard. Not everyone in a city. Everyone. But here is where it gets strange. Even in the absence of catastrophic disease, the genetics of the crew would degrade on their own. Dr. John Moore at the University of Florida has calculated that maintaining genetic diversity across a multi-generational population requires a minimum founding group of around 10,000 individuals. Dr. Frederick Marin at the University of Strasbourg, working with genomic modeling of generation ships specifically, has concluded that even larger numbers may be needed. Below those thresholds, harmful genetic variants accumulate. Inbreeding depression deepens. Birth defects, cognitive disabilities, and early mortality increase across each successive generation. The Toba supervolcanic eruption, roughly 74,000 years ago, reduced the entire human species to perhaps 10,000 individuals. The genetic bottleneck that event created is still detectable in human DNA today. We still carry its signature in the reduced variation that traces back to that near extinction. An interstellar ship carrying hundreds or even a few thousand people would face a bottleneck worse than Toba. Not a temporary one, a permanent one, self-reinforcing across every generation of the journey. And the psychology would fail before the genetics could even run its course. In 2010 and 2011, a joint project by Russia, China, and the European Space Agency called Mars 500 locked 6 volunteers inside a simulated spacecraft for 520 days. These were not ordinary volunteers. They were carefully screened for psychological resilience. They knew the experiment's duration in advance. They had the option to leave at any time. And they were not actually in space. They were in a facility in Moscow. The result was severe depression, disordered sleep that did not resolve, conflicts between crew members that approached violence. One participant refused to leave his quarters for months, 520 days, on Earth, with the option to walk out. Dr. Nick Canas, a psychiatrist who has studied astronaut psychology for decades, has described what he calls the Earth out phenomenon. It is the moment when Earth, which recedes across the early part of any deep space journey, finally crosses the threshold and becomes indistinguishable from any other point of light. For Apollo astronauts, Earth was always visible as a distinct blue marble. On an interstellar crossing, Earth would vanish entirely. Not diminish, vanish. Dr. Peter Sudfeld's research on sensory deprivation shows that the human mind requires environmental variation to maintain basic cognitive stability. Decades of unchanging stars through a viewport is not a minor inconvenience. It is an assault on the nervous system at a structural level. Antarctic research stations offer a partial analogy. Personnel stationed through the polar winter at remote Antarctic sites experience what researchers call winter over syndrome. Depression, anxiety, impaired judgment, interpersonal conflict. And this happens despite regular resupply, regular communication with home, and the knowledge that the season will end. An interstellar crew would have none of those anchors. They would also need to eat. The International Space Station grows small amounts of lettuce through its vegetable production system, but it requires continuous resupply from Earth. Every calorie the ISS consumes ultimately comes from somewhere else. Dr. Raymond Wheeler, working on NASA's Advanced Food Technology project, has estimated that feeding 6 people on a Mars mission would require a greenhouse roughly the size of a football field. An interstellar mission carrying thousands of people across centuries would need agricultural space larger than the island of Manhattan, sealed, self-sustaining, and immune to the slow degradation of closed ecosystems. Every closed ecology experiment attempted on Earth has failed. Biosphere 2 was the most ambitious attempt. Built in the Arizona desert at a cost of $200 million, it was designed to demonstrate that 8 people could survive for 2 years in a sealed, self-sustaining environment. The ecological science was the best available in the early 1990s. The team was committed. The project had unlimited sunlight from above and the full pull of Earth's gravity below. It collapsed. Oxygen levels dropped to dangerous lows. Crops failed. The ecosystem destabilized. The crew could not survive on what the sealed environment produced. On Earth, with sunlight, with gravity, in 2 years. The ISS recovers roughly 93% of its water through recycling systems. That remaining 7% must be resupplied from Earth. 7% sounds like a small margin. Across centuries in the interstellar void, with no resupply possible and no water sources within light years, 7% is the difference between survival and death. And if any of the crew tried to reach home for help, the answer could not arrive for years. A message sent to Earth from a ship approaching Proxima Centauri would take more than 4 years to arrive. A reply would take more than 4 years to return. Any crisis, any outbreak, any catastrophic system failure would be faced entirely alone. The ship would be severed from any knowledge or assistance that could reach it in time to matter. Now consider what surrounds that ship. Space between the stars is not empty. It looks empty. It registers as empty in the imagination. But the interstellar medium is threaded with diffuse matter, charged particles, and cosmic rays accelerated to near the speed of light by supernovas and black holes. At low speeds, This material is nearly harmless. At the speeds an interstellar ship would need to travel, it becomes something else entirely. Dr. Philip Lubin at UC Santa Barbara has modeled what happens to even a gram-scale probe traveling at 20% of light speed when it encounters interstellar dust. Each grain, a particle so small it would be invisible to the naked eye, strikes with an energy comparable to a nuclear explosion. Each impact blasts a crater. Across the course of an interstellar journey, the cumulative effect is total erosion. The probe does not arrive damaged. The probe dissolves, grain by grain, like a sandcastle taken apart by waves. Some scientists believe the density of the interstellar medium alone is enough to impose a practical speed ceiling of around 10% of light speed. Below that threshold, the bombardment is survivable, at least in the short term. Above it, the spacecraft is simply consumed by the medium it is crossing. But even at lower speeds, the hull is not safe. Dr. Paul Davies at Arizona State University has calculated what cosmic ray bombardment does to metal over centuries. The particles do not simply pass through. They transmute the atoms they strike, converting ordinary structural metals into brittle isotopes that the original alloy was never designed to contain. After a few centuries of exposure, a hull that was structurally sound at departure would become unpredictable. A minor impact that the original material would have absorbed without consequence could trigger catastrophic failure. No known material maintains its integrity over the millennia that a conventional speed interstellar journey would require. None. Not because we have not found the right alloy yet. Because the physics of sustained cosmic ray exposure rewrites the material at the atomic level, and there is no atomic structure that can sustain that indefinitely. The ship is hostile inside. Biology drifts, microbes mutate, minds fracture, ecosystems collapse, and the universe is hostile outside. Radiation accumulates, dust erodes, whole metals transmute into something no engineer specified. There is no safe enclosure. There is no configuration of metal and air and biology that resolves both problems at once. And that is before asking what waits at the destination. Set aside, for a moment, the physics and the biology. Set aside the radiation, the bone loss, the fracturing minds, the mutating microbes, the whole metals that the cosmos slowly rewrites into something brittle and unreliable. Those walls are real, but there is another wall standing independently of all of them. It does not care about propulsion systems or shielding designs or the genetic health of a founding population. It is the most ordinary question in the world. Who would pay for this? The Apollo program cost $25 billion in 1973 currency. In today's dollars, that is roughly $280 billion. That bought 12 astronauts a total of 80 hours on the lunar surface, a body 384,000 kilometers away. Work out the arithmetic slowly. That comes to approximately $23 billion per person delivered to the moon. The International Space Station has cost more than $150 billion to keep 6 people alive in low Earth orbit, a few hundred kilometers up. These are our 2 best data points, our most expensive, most ambitious, most sustained human spaceflight programs. And they are the baseline. Proxima Centauri is 110 million times farther than the moon. Not 10 times farther. Not 1,000 times farther. 110 million times. Scale the Apollo cost accordingly. Even if you assumed a million-fold improvement in efficiency, an engineering miracle beyond anything in human history, sending a single person to the nearest star would still cost more than the entire accumulated economic output of our civilization across thousands of years. The numbers do not bend. They simply grow until they lose contact with anything recognizable as a budget. But here is where it gets strange. Some proposals have tried to root around the scale problem by starting smaller. Breakthrough Starshot, the most serious modern attempt, begins with $100 million just for initial research funding. A full mission, launching gram-scale probes the mass of a paperclip, would require tens of billions more, and all of that investment buys a flyby. Probes that cannot stop. Probes that pass through the Proxima Centauri system in a matter of hours and continue forever into the dark. That is the best case scenario for the most ambitious, most generously funded, most technologically optimistic proposal on the table. A flyby, with probes lighter than a paperclip. A crewed mission is a different order of magnitude entirely. The Stanford Torus, a 1970s design concept for a rotating habitat supporting 10,000 people, was estimated at roughly $1 trillion in today's currency. For a structure in Earth orbit, not in interstellar space, an interstellar version, hardened against cosmic rays, capable of self-sustaining for centuries, would cost thousands of times more than that. The number detaches from meaning. It exceeds not just any national budget, but any reasonable projection of global wealth accumulation across centuries. Dr. Alan Bond, who led Project Daedalus, concluded that building even the unmanned probe his team designed would consume more resources than the entire global economy produces in a decade. His fuel requirements alone tell the story. 50,000 tons of deuterium and helium-3. Deuterium can be extracted from seawater with effort. Helium-3 barely exists on Earth at all. Obtaining it in those quantities would require strip mining the moon or harvesting the atmosphere of Jupiter. Not ambitious extraction operations, not larger versions of existing facilities. Planetary-scale industrial operations that do not exist, have never existed, and would themselves require decades and trillions of dollars to build before a single gram of fuel was ready. Dr. Robert Zubrin, who has spent decades calculating what interstellar missions would actually require, reached a harder conclusion. Building a single fusion rocket would consume more of certain rare elements than exists in Earth's accessible crust. We would run out before finishing one vessel. The ceiling is not financial, it is geological. The planet does not contain enough of what we would need. The gross world product is approximately $100 trillion per year. NASA, the world's largest space agency, operates on a budget of about $25 billion annually. That is roughly 0.025% of global GDP. Imagine redirecting 10% of all global economic activity toward interstellar travel. Every government, every economy, every institution, 10% of everything, sustained for centuries. That is politically impossible by any historical measure. And even then, the resource requirements of a genuine interstellar mission would not be met within any human timescale, which brings the problem to its sharpest edge. No human institution has ever sustained a project across centuries of continuous political will and funding. Lloyd's of London, founded in 1688, is 336 years old. It is the longest-lived commercial institution in the modern world, and it is still nowhere near the timescales an interstellar program would require. Not close, not approaching close. The historical record is clarifying. In the early 1400s, the Ming dynasty operated the largest fleet of ocean-going vessels in human history. The treasure fleets of Admiral Zheng He, 7 expeditions across decades, reaching as far as the east coast of Africa. Then a single emperor reversed the policy. The ships were left to rot. The maritime program that had no rival on Earth was abandoned because the cost exceeded any political consensus about its benefit. A single change in leadership ended it entirely. More recently, in 1993, the United States cancelled the superconducting Super Collider, a particle accelerator under construction in Texas. $2 billion had already been spent. Construction was underway. The scientific case for completing it was strong. Congress cancelled it anyway. $2 billion and a decade of work, abandoned. That project would have cost roughly $12 billion total, a fraction of the Apollo budget, a vanishing fraction of what any interstellar mission would require. Mars One, a private initiative that attracted enormous media attention for its plan to establish a human settlement on Mars, filed for bankruptcy in 2019. Mars is 400 times closer than Proxima Centauri. If we cannot sustain funding for a one-way Mars mission through a single decade, an interstellar program spanning centuries is not a planning problem. It is a category error. Wait, there is an economic argument that makes this even cleaner. Nobel economist Paul Krugman has pointed out that investment in Earth-based development always produces better compound returns than space investment at these distances. Dr. Robin Hanson has extended this further. Even a theoretically post-scarcity civilization, one with far more resources than we have today, would face the same calculus. Resources devoted to an interstellar mission would generate better returns if invested anywhere else. The compound interest logic does not favor departure. It favors staying and growing richer at home. Dr. Jeffrey Landis at NASA ran the most extreme version of this calculation. Imagine, he said, that a planet of pure gold orbited Proxima Centauri. Solid gold. The entire planet. Retrieving it, even accounting for the extraordinary value of that much gold, would cost more than the retrieved gold is worth by factors of millions. The journey is simply too expensive. There is no cargo rich enough, no resource valuable enough to make the economics work. Not even a planet of solid gold. The opportunity cost is worth naming plainly. The resources that a serious interstellar program would require, even a preliminary program, even the early infrastructure, could end global poverty, could accelerate climate solutions by decades, could fund medical research that would save hundreds of millions of lives. These are not abstract alternatives. They are real competing users for real resources. The question of who pays for an interstellar mission is also, necessarily, a question of what does not get funded instead. Physics said no. Biology said no. And now economics says no from a completely different direction. 3 independent walls, each one sufficient on its own. And none of them built from pessimism or failure of imagination. Each one is a careful reading of what the universe actually costs and what we actually have. The question has never been whether we lack ambition. We have never lacked ambition. The question is whether ambition, however genuine, however sustained, can move the numbers. And the numbers, across propulsion and biology and economics and institutional longevity, have so far given the same answer every time. But there is one more wall, and it does not involve physics or biology or money. It involves the destination itself. But there is a question sitting behind all of that, behind the propulsion and the biology and the economics. A question we have not yet asked directly. Not whether we can go, whether we should. And when you press on that question honestly, something unexpected happens. The reasons dissolve one by one. 3 motives are almost always offered when people make the case for interstellar travel: scientific research, resource acquisition, survival. Start with research. The argument is that we need to physically arrive at other star systems to understand them, to study them up close. But robotic probes already do this work. They do it without life support, without food, without water, without the years of psychological collapse we spent the last hour walking through. Every planetary mission in the last 50 years has been robotic. Every major discovery about the outer solar system came from machines. Increasingly capable machines, growing more sophisticated with every generation. We do not need human bodies to arrive somewhere to learn what is there. Resources are the second motive. The idea that distant star systems might hold materials we need, but this collapses even faster. Between the Moon, the asteroid belt, and Mars, our solar system contains more raw material than any conceivable human civilization could consume. The asteroid Psyche alone, a metallic body drifting in the asteroid belt, is estimated to contain enough iron and nickel to meet human demand for millions of years. We have not run out of solar system. We have barely started using what surrounds us. Then there is survival. And this is where the argument gets serious, because serious people make it. Stephen Hawking made it. Robert Zubrin makes it. Elon Musk has built a company around it. The core claim is this: Earth is fragile. Climate change, nuclear war, an asteroid impact, a gamma ray burst from a nearby stellar event. Any one of these could threaten civilization or the species itself. A backup colony, a planet B somewhere beyond Earth, is the only long-term insurance against extinction. It sounds rational. It might even be right as a general principle. But here is where it gets strange. The math does not save the argument. It breaks it. Earth's population grows by roughly 80 million people per year. Even the most optimistic vision of an interstellar colony would save thousands, perhaps tens of thousands. Against a species of 8 billion, That is not a rescue. It is a footnote. A colony that saves 10,000 people while 8 billion die is not a survival strategy. It is a rounding error with a rocket attached. Mass migration as a solution is even further from reality. To hold Earth's population constant by moving people off the planet, you would need to transport 80 million people per year to another world. Not someday in the distant future. Every year. Continuously. That number is not an engineering challenge. It is a statement about the category error at the heart of the argument. The problems we are trying to escape grow faster than any conceivable escape could move. And the timeline makes it worse. Suppose we identified a habitable planet 50 light-years away. Suppose we sent a probe in 2100. That probe would arrive around 2600. A follow-up colonization mission, if launched immediately, would arrive around 3100, 1,000 years from now. If the threat we are fleeing is climate collapse or nuclear war, or an asteroid on a collision course, we are not outrunning it. A 1,000-year escape plan does not protect against a century-scale catastrophe. Dr. Seth Shostak at the SETI Institute put it plainly. Radio communication, he has noted, is millions of times more cost-effective than physical travel for exploring what is out there. Any rational civilization would explore through signals and telescopes first, through spacecraft second, and through crewed interstellar missions almost never. The honest conclusion is this. Even the why dissolves on inspection. But let's say we set all of that aside. Let's say the motive is real and urgent enough. Let's say we find the energy, solve the biology, sustain the economics across centuries. There is still one more thing to reckon with, and it lives inside the physics itself. Time dilation is real. This is not science fiction. It is verified, tested physics, confirmed in atomic clocks aboard aircraft, confirmed in particle accelerators, confirmed in the daily corrections built into GPS satellites. Einstein's special relativity tells us that time slows for observers moving close to the speed of light, relative to observers who are stationary. Not as a perception, not as an illusion, as a physical fact, measurable and precise. The numbers are staggering. A spacecraft moving at 95% of the speed of light, traveling to a star 9.5 light-years away, would cover that distance in 10 years as measured on Earth. But the crew aboard would experience only about 3 years and 2 months. Not 10 years. 3. Move faster still. At 99% of light speed, time aboard passes 7 times more slowly than on Earth. At 99.99% of light speed, 70 times more slowly. At 99.9999999% of light speed, the dilation reaches a factor of 22,300. Time on Earth flows 22,300 times faster than time aboard the ship. At exactly the speed of light, which is physically impossible for any object with mass, time aboard would stop entirely. This means that in principle, a traveler moving close enough to light speed could cross any distance, 100 light years, 1,000 light years, more, in a brief subjective time. A human lifetime of travel could carry a crew across an enormous fraction of the galaxy. This is what science fiction reaches for. This is the dream. Wait. It is also the trap. Accelerating any mass to near light speed requires effectively infinite energy. We established that in detail. And the particle bombardment at those speeds, the interstellar dust grains arriving like continuous nuclear detonations against the hull, would destroy the ship and everyone aboard. Both problems are catastrophic on their own. Together they make the relativistic loophole close almost as fast as it opens. But here's where it gets strange. Even if both problems were somehow solved, even if the energy existed, and the shielding worked perfectly, the traveler would still be severed from home in a way that empties the journey of meaning. A crew departing Earth at near light speed would know, with certainty, that they would never see their families again. Not because the journey is dangerous, because of what time dilation does to the world they leave behind. 3 subjective years of travel might correspond to decades on Earth. A longer journey might correspond to centuries. On return, if return were even possible, they would not find the world they left. They would find a world separated from them by generations. a society they would not recognize, a civilization that had moved on entirely. No letters, no news, no shared culture, no continuity, no commercial enterprise sends cargo it can never communicate with again. No government funds missions whose results return after the financiers have been dead for 1,000 years. No institution, however powerful, binds itself to an outcome it cannot witness, cannot respond to, cannot use. The Star Trek vision of an interstellar civilization, trade between systems, shared political structures, a united federation of species exchanging ideas and goods and ambassadors depends on a kind of human connection that time dilation makes impossible. Not difficult, impossible. There is no federation if every ship that leaves does not come back to the same era. There is no trade if every cargo takes centuries. There is no shared culture if every conversation takes 8 years round trip. Any spacecraft moving at relativistic speed becomes a world unto itself, without homeland, without past. The crew does not travel to another civilization. They become a civilization of one ship, cut off from everything that gave departure its meaning. And that may be the deepest wall of all. Not the energy, not the biology, not the economics. The fact that even in the most physics-favorable scenario we can construct, the traveler arrives, if they arrive, as someone who has lost everything the journey was supposed to be for. The question was never only whether we can reach the stars. It was whether reaching them, under any conditions physics permits, leaves us with something we recognize as a journey rather than an exile. That question of exile versus journey does not end with one hypothetical traveler. Lift your gaze wider. Not toward the stars we are trying to reach, but toward whatever might also be looking back. In 1950, the physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos and asked a question so simple it should have had a simple answer. If the universe is so vast and so old, where is everybody? That question became known as the Fermi paradox, and the longer we search, the heavier it gets. Here is what the numbers say. The Kepler Space Telescope and the TESS mission have now catalogued more than 5,000 exoplanets, worlds orbiting other stars. Statistical models built from that data suggest our galaxy alone contains at least 300 million potentially habitable worlds. 300 million. Not in the whole observable universe. In this galaxy, in our neighborhood, the James Webb Space Telescope has already detected water, methane, and other biosignature gases in multiple exoplanet atmospheres. These are the chemical markers we associate with living processes. Life, according to the data, should not be rare. Life should be everywhere. And yet the universe is silent, not quiet, silent. 63 years of sustained listening have returned nothing. The SETI program, the search for extraterrestrial intelligence, began scanning the sky in 1960. The Allen Telescope Array now monitors millions of star systems continuously. Breakthrough. Listen, funded at $100 million, uses the most sensitive radio telescopes on Earth. It could detect a transmission from thousands of light years away. 60 plus years of effort. Nothing. Not a signal. Not an artifact. Not a pattern that required intelligence to explain. Nothing. But here's where it gets strange. The silence is not just about signals. It is about presence. Dr. Anders Sandberg at the Oxford Future of Humanity Institute worked through a thought experiment. Imagine a single civilization, somewhere in our galaxy, achieved interstellar travel 1 billion years ago. Even if they expanded slowly, moving at just 1% of the speed of light, the mathematics are unforgiving. At 1% of light speed, they would have colonized the entire galaxy long before our sun even formed. Not most of it. All of it. The galaxy is old enough and large enough that even a glacially slow expansion, by cosmic standards, would fill it completely over 1 billion years. If anyone had ever done this, Earth would show evidence of past visitation. Ancient infrastructure, anomalous materials, something. There is nothing. No signals, no probes, no megastructures, no ruins, no fingerprints on the geological record. The Earth has been here for 4.5 billion years. It has been habitable for most of that time. and there is no sign that anyone has ever come. In 2018, Dr. Gavin Schmidt and Dr. Adam Frank examined this question directly in what they called the Silurian hypothesis. They asked whether an ancient industrial civilization on Earth itself could have existed and gone undetected. The answer was that it would leave traces, plastic particles embedded in sediment layers, signatures of nuclear fallout, patterns of mass extinction tied to industrial-scale chemical release. These markers would persist in the geological record for millions of years. Scientists have searched for them. They are not there. No ancient civilization on Earth. No visiting civilization from elsewhere. Nothing. Then came 2017. An object designated Oumuamua entered our solar system from interstellar space. The first interstellar visitor we had ever confirmed. It moved strangely. It accelerated slightly as it departed, in a way that did not fit neatly with known natural explanations. Dr. Avi Loeb at Harvard raised the possibility that it could be an artificial object. A light sail, perhaps. Discarded technology from another civilization, drifting through space. Follow-up analysis by ESA and other teams concluded otherwise. Oumuamua was almost certainly natural. The most consistent explanation was a low-density fragment, possibly a piece of a comet or planetary body with an unusual shape and composition that accounted for its strange motion. Not alien, not artificial. But what Oumuamua proved was something important regardless. Interstellar objects pass through our solar system. The medium between stars is not impenetrable. Things can travel between star systems over cosmic timescales. If any civilization had ever sent probes into interstellar space, some of those probes should have drifted through here by now. The solar system has been here long enough. The galaxy is full enough. By pure probability, we should have seen something. We have not. Now come the numbers. In 1961, astronomer Frank Drake developed an equation to estimate the number of communicating civilizations in our galaxy. Updated with everything we know from Kepler and TESS and Webb, the Drake equation suggests somewhere between 1,000 and 100 million civilizations should exist in the Milky Way right now. The range is enormous because our uncertainty is enormous, but even the lowest end of that estimate is 1,000. 1,000 civilizations in this galaxy alone. And Breakthrough Listen can hear transmissions from thousands of light years away. 1,000 civilizations. 63 years of listening. Nothing. Wait. There is a framework that makes the silence coherent. Dr. Robin Hanson proposed it in 1998. The Great Filter. The idea is straightforward. Somewhere between dead matter and an interstellar civilization, there is at least one step that is nearly impossible. A transition so difficult that almost nothing gets through it. The great question, Hansen noted, is whether that filter is behind us or ahead of us. Most scientists hope it is behind us. The origin of life from chemistry. The evolution of complex cells from simple ones. Consciousness. These are plausible candidates for steps so difficult that only we, or only very few, have cleared them. If the filter is behind us, we might be nearly alone and our future is open. But what if the filter is ahead? What if the nearly impossible step is interstellar travel itself? Consider what every previous section of this journey has established. The energy requirements exceed what any single star civilization can generate. The biological cost makes biological beings incompatible with the journey. The economics outlast any institution or political structure that could fund them. The physics of time dilation severs the connection between the traveler and the civilization that sent them. Each of these walls is independent. Each is sufficient on its own. Together they form something that looks less like a technical challenge and more like a universal law. Dr. Milan Čiriković at the Astronomical Observatory of Belgrade put a name to the underlying logic. The astrobiological Copernican principle. The idea is simple. Earth is not special. Humanity is not exceptional. We are a typical outcome of a universe that produces planets and chemistry and minds. If that is true, then whatever limits us limits everyone. We are not uniquely cursed by our physics. We are ordinary. Our physics is the physics. Our walls are everybody's walls. That changes the Fermi paradox completely. The silence is not a mystery. It is confirmation. The universe might be full of intelligent life. Every civilization reaching the point we have reached, looking up at the same night sky, building the same telescopes, doing the same mathematics, arriving at the same conclusion. Not that the stars are unreachable for them specifically, that the stars are unreachable, universally, structurally, not an engineering problem waiting for a solution, a hard boundary written into the laws that govern mass and energy and time, the cosmic quarantine, not imposed by any authority, not maintained by any power, maintained by physics itself, every mind in the galaxy confined to its home system by the same insurmountable equations. The Great Filter was never a catastrophe waiting ahead of us. It was never a weapon or a disease or a war. It was the speed of light. It was the rocket equation. It was the cost of decades or centuries in transit against the biological clock and the institutional clock and the civilizational clock. The Great Filter is what we have been describing for the past several hours. And the silence of the universe is not an absence. It is an answer. The question is what we do with that answer. That may be where this journey has been heading all along. That silence has a shape. Stay with it a moment longer, because it points somewhere specific. Not outward toward the stars we cannot reach, inward toward the world we already have. And when you look closely at what the universe has actually prepared for us, the silence deepens in a different way. Here is what the numbers say. 75% of all stars in the galaxy are red dwarfs. Small, dim, cool, and almost immortal. They burn for trillions of years, far longer than our sun will. They seemed, for a long time, like ideal candidates, stable, abundant, everywhere. Surely some of their planets harbor life, but here is where it gets strange. Dr. Manasvi Lingam and Dr. Avi Loeb studied what life on those planets would actually face, and the picture changed completely. Red dwarf planets sit so close to their stars that gravity locks them in place. One side bakes in permanent daylight, the other freezes in permanent night. The temperature gradient between those two hemispheres is severe enough to drive winds that would tear apart anything resembling a stable biosphere. And the stars themselves are not calm. They flare, repeatedly, violently, bathing their closest planets in bursts of radiation that would strip an atmosphere and irradiate a surface. Even if life found a way to begin, Lingam and Loeb concluded, the path to technological civilization on a tidally locked, flare-irradiated world may be closed. Not merely difficult, closed. And red dwarves are only part of the constraint. Dr. Guillermo Gonzalez at Ball State University mapped what he called the galactic habitable zone. The idea is straightforward. Position a star too close to the galactic center, and it sits within reach of radiation from the supermassive black hole. Supernovas in that crowded region detonate frequently, sterilizing nearby worlds with X-rays and gamma radiation before complex life can take hold. Position a star too far from the center, and the heavy elements needed to build rocky planets simply are not there. The galaxy's outer reaches are chemically sparse. Rocky worlds require iron, silicon, magnesium, calcium. Those elements were forged in earlier generations of stars and scattered through the galaxy over billions of years, but unevenly. The outer edges never accumulated enough. The result? Only about 10% of stars in the galaxy occupy the zone where all the conditions align. Not slightly fewer than we hoped. 1 in 10. Now compress the filter further. The ALMA Observatory, which combines the light of dozens of radio telescopes to form a single massive eye, has studied the swirling disks of gas and dust from which planets form. What it found was chaos. Planet formation is not orderly. Worlds collide. Worlds are flung outward. The microlensing observations in Astrophysics Survey extended that picture further and found something that stops you. Billions of rogue planets drift through the galaxy entirely untethered to any star. Frozen. Dark. Dead. Worlds that formed and were then ejected, wandering the interstellar void without a sun. There are more of these drifting bodies than there are the stars in the Milky Way. Most of what forms does not survive in a form that could support life. Which brings us to the exoplanets we have actually studied, the ones inside habitable zones, around stable stars, at promising distances. Surely some of those are like Earth. Here's what scientists believed at the time: 5,000 exoplanets catalogued, headlines describing Earth's cousins, potentially habitable worlds, candidates for life. The optimism was real, and then, on closer inspection, the picture changed. TRAPPIST-1e was among the most celebrated, a rocky planet in the habitable zone of its star, orbiting at a distance that put liquid water within reach. It was hailed as one of the most promising exoplanets ever found. But TRAPPIST-1e orbits a red dwarf. It is tidally locked. It is bathed in radiation. Whatever atmosphere it has, if it has one, is nothing like Earth's. Not a cousin. Not remotely similar. A world that shares a category on a checklist and almost nothing else. Kepler 452b was described as Earth's twin. It orbits within its star's habitable zone at roughly the right distance. But the star is significantly older and significantly different from our Sun. The radiation it emits would make photosynthesis, as we know it, impossible. The conditions that allowed plants and algae and ultimately every complex organism on Earth to draw energy from sunlight simply do not apply there. Every exoplanet we have studied closely has reinforced the same conclusion. The category of potentially habitable contains many worlds. The category of actually habitable by life as it exists and operates on Earth may contain far fewer. We do not have to look to distant star systems for cautionary examples. They are in our own backyard. The Venus Express mission, operated by the European Space Agency, returned detailed measurements from the planet next door. Venus is roughly the same size as Earth. It occupies a similar position in the solar system. It formed from the same raw material at the same time. And it is a ruin. The surface temperature is 460 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is 90 times what you would experience standing on Earth. Sulfuric acid forms in the clouds and rains downward, evaporating before it reaches the ground. A day on Venus is longer than its year. It rotates so slowly that the sun rises in the west. Earth could have become this. The margin between the two outcomes may have been small. A slightly different early history, a slightly different distance from the sun, a slightly different chemical balance in the ancient atmosphere. Mars sits on the other side of that narrow range. The Perseverance rover has found evidence of ancient water, organic molecules, the chemical signatures of a world that once had rivers and lakes, and the raw material of biology. But Mars now is a frozen, irradiated wasteland. Its atmosphere is 100 times thinner than Earth's. The Martian core died early, billions of years ago. When it did, the planet's magnetic field collapsed. With no magnetic field, the solar winds stripped the atmosphere away over millions of years. The water evaporated or froze underground. The surface became exposed to radiation that would destroy any exposed organism. Mars did not fail because it was never promising. It failed because it lost the specific chain of conditions that Earth maintained. Dr. Peter Ward and Dr. Donald Brownlee assembled the full picture in what they called the rare Earth hypothesis. Complex life, they argued, does not require merely a habitable zone and liquid water. It requires a stable star that does not flare destructively, a large moon to stabilize the planet's axial tilt, preventing wild swings in climate, a Jupiter-sized planet in the outer system to deflect incoming asteroids, plate tectonics to recycle carbon and regulate temperature over billions of years, the right planetary mass to hold an atmosphere, the right chemistry in the crust and ocean. Change any of these factors by a few percent, and the long stable period required for intelligence to evolve does not arrive. Dr. Dave Waltham at Royal Holloway University carried this further. Earth's remarkable stability, the billions of years of relatively gentle conditions that allowed life to complexify from microbes to minds, required a coincidence of factors so specific that it may never have been replicated anywhere else in the observable universe. Not improbable in the sense of unlikely. Improbable in a deeper sense. Perhaps singular. Dr. Charles Lineweaver at the Australian National University offers one final piece. Earth-like planets around Sun-like stars, he calculated, formed on average 1.8 billion years before Earth did. If interstellar travel were possible for any of the civilizations that might have evolved on those older worlds, they would have had a 1.8 billion year head start. They should have colonized the galaxy many times over before our sun even ignited. The absence of any sign of that expansion is not a puzzle. It is data. It confirms, from a completely different angle, what the physics already told us. Some have proposed that older civilizations deliberately avoid us, a kind of cosmic wildlife preserve. Dr. John Ball suggested this in 1973, what he called the zoo hypothesis. But that explanation requires perfect coordination across millions of civilizations over billions of years, all maintaining the same policy without a single defector. Given that communication between those civilizations would be constrained by the same light speed limits we face, achieving that coordination is impossible. The simpler answer is the one the evidence points to consistently. They cannot reach us. We cannot reach them. Not because of any choice or policy, because of physics. Earth is not one habitable world among many, waiting to be joined by colonies on planets orbiting other stars. It may be the habitable world, the one place in a vast and largely hostile universe where the right conditions held together long enough for something like us to exist. And what we do with that singular piece of luck is a question the universe will not answer for us. That question is the one this entire journey has been building toward. And the answer begins not with hope or consolation, but with honesty. The case is complete. Distance, physics, biology, economics, time, the cosmic silence, the rarity of habitable worlds. Every angle converges on the same point. We will not leave the solar system, not in any meaningful sense, not in any human time frame, not ever, in all probability. Sit with that for a moment. It is crushing on first hearing. Everything we have been told about the human story suggests expansion. Out of Africa, across the oceans, into orbit, toward the stars. The narrative has a direction, and that direction is outward. To be told the outward motion stops here, at the edge of our own small system, in this unremarkable corner of a middle-aged galaxy, feels like a sentence. A closing of something that was supposed to stay open. But here is where it gets strange. The moment you stop fighting the conclusion and simply stand inside it, something shifts. The impossibility does not feel like a wall anymore. It feels like a frame. And what is inside the frame is something we have been too busy dreaming of leaving to fully see. Earth is not a cradle we will eventually leave. It is our home. The only one. Forever. That word deserves to land. Not approximately forever. Not forever until something better comes along. The physics we have spent this entire journey examining makes the word precise. This is it. This particular planet, this particular atmosphere, this particular improbable arrangement of water and rock and biology. Ours. Permanently. And when you understand that, something strange happens to the distances between stars. They stop looking like walls. Dr. Peter Ward at the University of Washington has argued that Earth's biosphere is not one version of life that could easily be replicated elsewhere. It is the product of a specific, unrepeatable sequence. The Great Oxygenation Event, 2.4 billion years ago, when photosynthetic bacteria flooded the atmosphere with oxygen and killed most of the life that existed before them, setting the conditions for everything that followed. The asteroid impact 66 million years ago that ended the dinosaurs and cleared the space for small mammals to diversify into every ecological niche on the planet, eventually producing us. Change either of those events slightly, and we do not exist. Change them more, and nothing like us exists. The sequence cannot be recreated. Not on another world, not in a laboratory, not by any intelligence however advanced. Earth's specific history is not a template. It is a singularity. The vast distances between stars, then, are not barriers preventing civilizations from finding each other. They are moats protecting the unique and unrepeatable diversity of cosmic evolution. If the distances were smaller, if travel were easy, expansion would homogenize the galaxy. Every local solution, every singular chain of contingency, every strange and unrepeatable accident of chemistry and geology and mass extinction would be overwritten by whichever civilization arrived first with superior technology. The isolation does not imprison life, it protects it. But the reframing goes deeper than ecology. It reaches into what we are. We are not adapted to Earth. That framing is already wrong. Adaptation implies we existed somewhere else and then adjusted. We did not adjust to Earth. We are Earth, temporarily organized into a pattern capable of consciousness. Every atom in your body except hydrogen was forged in the nuclear furnaces of stars that died before our sun was born. The iron in your blood came from a supernova. The calcium in your bones came from the collapse of something enormous. The oxygen you are breathing right now has circulated through the lungs of organisms that lived and died hundreds of millions of years before the first human took a breath. Every molecule of water in your body has passed through countless living beings across geological time. You are not visiting this planet. You are a temporary expression of it. Dr. Lynn Margulies understood this more precisely than almost anyone. Her work on endosymbiosis revealed that every cell in your body is not a single organism, but a community of formerly independent organisms that merged billions of years ago. The mitochondria that power your cells were once free-living bacteria. They were absorbed, not destroyed, and the merger produced something neither could have been alone. Margulies spent decades arguing that this is the pattern of life itself, not competition and escape, integration and cooperation. Survival does not come from fleeing a system. It comes from becoming part of one. The astronauts understood it too, though it took leaving Earth to show them. Edgar Mitchell walked on the moon in 1971. He was a trained engineer and Navy test pilot, not a poet, not a mystic. But on the return journey from the lunar surface, looking at Earth suspended in the blackness, he experienced what he later described as an instant global consciousness. A sudden, overwhelming recognition that everything he was looking at, the planet, its life, the relationships between living things, formed a single unified system of staggering beauty and fragility. He came back not wanting to leave Earth. He came back desperate to protect it. That is the overview effect. Astronaut after astronaut reports the same thing. Not a desire to explore farther, a sudden, almost painful love for the one place they came from. Dr. Giulio Tononi's integrated information theory suggests that consciousness arises wherever information is processed in a sufficiently complex and integrated way. The human brain qualifies, but Tononi's framework implies that Earth's biosphere, with its billions of interacting species and feedback loops and chemical signals passing between organisms across continents, may itself possess a form of consciousness we can barely imagine. Not consciousness like ours, something older and stranger and larger. We are not the planet's passengers. We may be something closer to its nervous system. And then, consider what we would do to that system if we genuinely tried to leave it. The resources required for a serious interstellar attempt would not simply be expensive. They would be devastating. Strip mining the moon for materials, building massive orbital infrastructure consuming rare elements in quantities that exceed Earth's accessible crust, launching thousands of rockets. The attempt to abandon Earth would require the systematic destruction of the planetary systems that sustain it. We would devastate the biosphere trying to escape the biosphere. The impossibility of interstellar travel may not be accidental. It may be Earth's own defense mechanism. A species smart enough to dream of stars, but not yet wise enough to cherish home would, given the chance, destroy its home in the attempt to leave it. The physics prevents that. The equations are not our enemies. They may be our guardrails. In 1990, the Voyager 1 spacecraft turned its cameras back toward the inner solar system from a distance of 6 billion kilometers. What it photographed became one of the most consequential images ever made. Earth appeared as a pale blue dot, a fraction of a pixel, suspended in a shaft of scattered sunlight. Carl Sagan looked at that image and wrote words that have not lost their weight in the decades since. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that mote of dust suspended in a sunbeam. not a launching pad. A home. What could we do if we turned the resources of interstellar ambition back toward that dot? Dr. Martin Rees, the astronomer royal, has pointed out that we are living in a golden age of cosmic discovery that requires no physical travel. Dark matter, dark energy, quantum entanglement, gravitational waves, the atmospheres of planets orbiting distant stars, all of it detected from here. From this planet, with instruments built on this surface and in this orbit, we could decode the languages of whales and dolphins. We have known for decades that these animals communicate in patterns of extraordinary complexity. We have never seriously tried to understand what they are saying. We could restore extinct species whose loss we still feel as a kind of grief. We could rebuild cities so they enhance ecosystems rather than replace them. The inner expansion available to us, through consciousness, through science, through the complexity of our own biology and our own planet, is not a consolation prize for failing to reach the stars. It is the actual prize. Dr. Nick Bostrom's simulation hypothesis raises a stranger possibility, that interstellar travel may be a deliberate constraint in the architecture of reality, like a boundary written into the rules of a designed system. A character in a video game cannot leave the map. Not because of a wall, because the map is the extent of what exists. This remains speculation, but it is a speculative idea that fits the evidence as well as any other. What does not remain speculation is this. The greatest human achievements did not emerge from escape. Buddha sat under the Bodhi tree in a specific place and found something that changed the world. Einstein worked out the structure of space-time in Berlin, a particular city in a particular century, surrounded by particular conversations and particular problems. Shakespeare wrote in London, a place soaked in the specific human noise of a specific historical moment. Every depth of insight we have ever reached came from deep engagement with a particular place, not from leaving it. The Lakota people have a phrase, mitakuye oyasin, all my relations. It is a recognition that the self is not separate from the web of living things around it. This was not a scientific discovery. It was millennia of careful attention to what existence actually feels like when you stop trying to escape it. Modern biology is now catching up to what that phrase describes. Doctor. James Lovelock proposed the Gaia hypothesis, the idea that Earth is a self-regulating living system, that its atmosphere, oceans, and biosphere interact to maintain conditions suitable for life. When he first proposed this in the 1970s, scientists dismissed it as mysticism. The evidence since then has been harder to dismiss. Earth survived the Paleocene-Eocene thermal maximum 56 million years ago, a period of runaway warming that reshaped the planet. It survived the Great Dying 252 million years ago, when 90% of all species on Earth went extinct. The planet survived. It regulated. It recovered. Not because Earth is kind, it is not. Because Earth is a system of staggering complexity and resilience, one that took billions of years to build and cannot be replaced by anything we could engineer or anywhere we could go. Feel the gravity holding you right now. It is not a trap. It is the same force that holds the atmosphere against the surface, that keeps the water in the oceans, that makes the blood move through your body. Breathe. The air entering your lungs has circulated through dinosaur lungs and through the bodies of organisms that lived in the primordial ocean before the first multicellular creature existed. You are breathing the accumulated exhalations of 4 billion years of life. The stars are not destinations. They are reminders. They are the furnaces that made the atoms your body is built from. They are the evidence that matter has a history, that the universe is not static and indifferent but generative and strange and ongoing. They are worth studying, worth understanding, worth spending an entire civilization's curiosity on. We will never leave our solar system. And that is the most beautiful truth in the universe. We are home. We have always been home. Home is all we will ever need. The question the universe cannot answer for us is not whether we can leave. It is whether we are willing to stay, and whether we can learn finally to be worthy of the extraordinary, unrepeatable, catastrophically unlikely place we have somehow ended up.